Hey everybody, this is Reed from Shayla Skies Aviation, and welcome back to Aviation Knowledge. This will be video 3 in our series covering how lift is created and the science behind kind of how it works. If you haven't checked out video 2, I'll leave a link either in the description or up above. I highly recommend checking that out to understand some of the terms we're going to use in today's video. But without further ado, let's get right on into it. To get started, we're going to talk about our first term for today, which is fluid. What is a fluid? More often than not, when you first think of the term fluid, you think of water or some other kind of liquid, right? But fluid is actually split into multiple different things. Yes, liquid and water and things like that are considered a fluid, but also air is considered a fluid as well. The definition of a fluid is a substance that has no fixed shape and takes the shape of its container. That means that both a liquid and a gas fall under the definition of a fluid. For example, if we look at a cup filled with water, that water that we poured in there is going to take the shape of the cup. If we take, let's say, air and we put it into a scuba tank, we're taking that air and putting it into a container, and it's going to take the shape of that container. So that's how we know air is a fluid. So one of the main points today we're going to talk about is something called Bernoulli's principle. So Bernoulli's principle is the idea that as a fluid increases velocity, the pressure of the fluid decreases. In today's lesson, fluid will refer to air. If you remember, air is considered a fluid, so all of Bernoulli's principle is going to have an effect on flowing air. But what does Bernoulli's principle actually mean? So to explain what Bernoulli's principle is and give you an example, we're going to use something called a Venturi tube. So a Venturi tube was designed by Bernoulli, the man who discovered Bernoulli's principle. And all it is a tube that has an open ends on both the front and the back, but constricts as it passes through the tube. So it gets narrower and then it goes back to the original size. And we're going to show how that demonstrates Bernoulli's principle. So this is our little Venturi tube. For example, today we're going to say these are going to have a funnel that's going to direct our air into this Venturi tube. So the air is going to be within here, and it's going to be forced through this Venturi tube. So let's go through the process and show Bernoulli's principle. So we start off here at the beginning. We have air, or air currents, you can say. Down here you can see that describing these air currents is that it has a slower velocity, velocity meaning speed, it's going at a slower speed, and it's got a higher pressure. So the pressure of this air is relatively higher. So what happens as this air is flowing from left to right, it's going to get closer and closer together and begin to kind of squeeze into this Venturi tube. As it continues, it's going to get squeezed and squeezed and squeezed, and as that air is going to this Venturi tube, it is going to increase its speed or increase its velocity. The reason it increases its velocity is because the air flowing through it has to be flowing at the same speed on the inlet side as the outlet side. So the only way to get this volume of air through this gap at the same rate as here and at the end is it's going to have to speed up to put enough air through to make it even. So as this air flows through our Venturi tube here, it increases that velocity. As that velocity increases, because Bernoulli's principle, as the velocity of a fluid increases, the pressure decreases, it's going to result in a lower pressure state within this Venturi tube right here. So this area has low pressure compared to the entry air that has a higher pressure, and that's all because of Bernoulli's principle. So as it continues to flow, you can see passing through the Venturi tube, it's going to separate back out into its typical flow, and at the end it's going to reach the same velocity and that higher pressure it started with. So as the air starts, higher pressure gets squeezed into the Venturi tube, forcing it to go faster. As it goes faster, it decreases pressure, and then as it exits, it fills back up that extra space and then slows down and goes back to that high pressure state. So that is going to be Bernoulli's principle. And this principle is extremely important to how we fly. So this seems all kind of random. What kind of tube are we using to fly? Well, if we go back here and take off all the stuff we just added, get back to just our Venturi tube, I want you to take a look at something. So if we have this Venturi tube, and you're saying it looks maybe a little bit familiar, well, if we take the top portion of this Venturi tube off and a little bit off the bottom, let me know what you think this looks like. If you guessed the wing of an airplane, you'd be right. So that bottom kind of portion of that Venturi tube is kind of very similar to what an airfoil looks like. The reason they are similar is because an airfoil tries to take advantage of Bernoulli's principle, just like the Venturi tube. This is what creates our main source of lift. So now that we understand the principle that a airfoil, or our wing, is very similar to that of a piece of the Venturi tube. So it's going to have the same effects as the Venturi tube and Bernoulli's principle. So let's talk about that. I'll just give you a quick example of how that might work. So we've got our plane here, our plane wing. So I'm going to get rid of this just so you can see a little bit better. But let's take that same example with the air coming towards the Venturi tube, or in our case a wing. So as air flows towards our airfoil or our wing, that air is going to reach the wing, and because it can't go through it, it's going to curve and go around it, like so. So as it hits this top, and then the air below it is going to kind of route around and is going to have a lot less resistance. So what happens as this air is directed over the curved surface of our airfoil on the upper surface, what happens is that same effect of Bernoulli's principle occurs. As it hits this top part of the wing, it's going to speed up in this region right here. The reason it speeds up is similar to the reason that the Venturi tube speeds up its air. Using the same idea that the amount of air at the beginning and the end of its path have to be equal, the wing itself causes a disturbance for the air flowing over it, aka the wing takes up some space that doesn't allow for the air to flow. You see, it can't flow through the solid object. This causes the flow of air to be constricted up above the wing, very similar to how it was constricted in the Venturi tube. This is what speeds it up. So as that air flows over the top of the wing, that's going to increase the speed, creating a low pressure. I'm going to use a different color here. A low pressure here. Associated with that low pressure, on the underside of the wing, you're going to have a relatively higher pressure. The reason you're going to have this higher pressure is because it is not receiving Bernoulli's principle. So comparing the two, the air from the top to the air to the bottom, the air from the bottom stayed about the same, but is going to be a higher pressure because the air going over the top is lowered because of Bernoulli's principle. And one concept that you can see here that is going to be extremely important is the idea that the high pressure air wishes to go to the low pressure air. So if you've ever experienced, let's say, a tire going flat. So in my example here, you can see that the tire is being filled with high pressure air, and at some point it cannot hold that high pressure air and it bursts. And that is going to show you as it bursts how high pressure air flows to low pressure air. Because the pressure in the tire is so high compared to the outside, it's pushing and pushing and pushing and trying to get to that low pressure and explodes out, and you can even see some of that air visibly moving from that high pressure environment to that low pressure environment. So coming back to our airfoil here, the same principle applies. So we have high pressure under the wing, low pressure above the wing. So all this high pressure is going to be trying to go to this low pressure above the wing. So it's going to be trying to flow towards that low pressure. But what happens is there is a wing in the way, and that air can't get to the low pressure, but it really, really wants to. So it's going to start providing a force on the underside of the wing, pushing up on the wing, trying to get to this low pressure. And that is the main source of lift. So because that high pressure is pushing to get to that low pressure, that is what gives us our lift force, or I should say the main component of our lift. So that high wanting to get to the low causes lift. The reason why there's a low pressure area and a high pressure area is because of Bernoulli's principle, in the way the airfoil is shaped creates a low pressure zone above the wing, which again the high pressure pushes up on the wing to try and get to that low pressure, resulting in lift. So that's the main cause of lift on an airfoil. There are a couple additional kind of, you could say, aids or components of the lift that aren't the main driving force for what cause lift, but add to what already exists here between these high and low pressure zones. So let's go and talk about that now. So the first example we're going to use for an additional component of lift, although it's not the main component, it is something we need to talk about. And this interaction has to do with when air hits the bottom of an airfoil. So when air is traveling towards this airfoil and it impacts the bottom of it, it is redirected downwards, as you can see here. So as it impacts the bottom, it's redirected downwards from the airfoil. As a result, Newton's third law comes into effect. So every action has an equal and opposite reaction. So as we have force going downwards, we're going to have force in the opposite direction. So that force in the opposite direction is going to push up on our airfoil and create lift, an additional source of lift. An example of this in real life that you might be able to see or test out if you haven't already is if you've ever stuck your hand outside of a car window. If you incline your hand, similar to that of our airfoil we talked about, you can notice that your hand wants to go up or climb up towards the top of the window. The reason that happens is because of this right here. As that air is hitting the bottom of your hand, it's redirected down, providing an upwards force on your hand, causing it to go up. So that's our first concept that is an additional component of lift. Our next one occurs with the redirection of airflow. So as air comes towards our airfoil and it intercepts the airfoil and flows around it, you can see that the air itself changes direction. So instead of just going over the airfoil and continuing in the same direction, it is redirected slightly downwards. Because of that, at the trailing edge of our airfoil, you can see that there is a force of air flowing slightly downwards. As a result, because of Newton's third law, we are going to have an equal and opposite reaction to that force. as seen here, that is going to help us generate a little amount of lift. So we have all this force, but let's zoom in here on one of them. So you can see here that equal and opposite force is applied as demonstrated by this green arrow. And we can break that down into two components. So we have a horizontal component and a vertical component. So even though this green force, or this force, is very slanted, it's not directly up and down, it's going to have a little bit of upwards force because it's not directly parallel or aiming down. So let's say this is parallel to the ground. So as it's slightly pointed up, we are going to have a slight amount of additional lift. So that's where that additional lift comes from, is that vertical component, because it is pitched higher than that would be level. So that's how we get a little bit of lift as a result of the redirection of airflow flowing off the back of our airfoil, and as a result of that, what's called downwash coming off the trailing edge of the airfoil. Well, that's going to wrap up today's video on how lift is created. There will be another video coming out soon going over something called the lift formula and the associated ways pilots can change the amount of lift we generate. But if you enjoyed the video, leave a like. It lets me know you're getting some use out of the video, and leave a comment if you have future suggestions or questions. Without further ado, I'll see you next time. See ya!